Hello? In this video, we're going to review the fundamental concept of PID control implementation. We're going to start looking at the two basic concepts of automatic control strategies. Two concepts provide the basis for most automatic control strategies, which are, first, feedback closed-loop control, and second, feed-forward open-loop control. Among these two, feedback control is the more commonly used technique of the two, and is the underlying concept on which most automatic control theory used to be based. Feedback control maintains a desired process condition by measuring that condition, comparing the measurement with the desired condition, and initiating corrective action based on the difference between the desired and the actual conditions. The only real distinction between the manual and automatic means of controlling the heater is that the automatic controller is more accurate and consistent, and is not as likely to become tired or distracted. Now look at the figure on the right. The feedback strategy is very similar to the actions of a human operator attempting to control a process manually. Consider the control of a direct contact hot water heater. The operator would read the temperature indicator in the hot water line and compare its value with the temperature desired. If the temperature was too high, he would reduce the steam flow, and if the temperature was too low, he would increase it. Using this strategy, he would manipulate the steam valve until the error is eliminated. An automatic feedback control system would operate in much the same manner. The temperature of the hot water is measured, and a signal is fed back to a device that compares the measured temperature with the desired temperature. If an error exists, a signal is generated to change the valve position in such a manner that the error is eliminated. The only real distinction between the manual and automatic means of controlling the heater is that the automatic controller is more accurate and consistent and is not as likely to become tired or distracted. Otherwise, both systems contain the essential elements of a feedback control loop. Feedback control has definite advantages over other techniques in relative simplicity and potentially successful operation in the face of unknown contingencies. In general, it works well as a regulator to maintain a desired operating point by compensating for various disturbances that affect the system. And it works equally well as a servo system to initiate and follow changes demanded in the operating point. Feed-forward control is another basic technique used to compensate for uncontrolled disturbances entering the controlled process. In this technique, the control action is based on the disturbance input into the process without considering the condition of the process. In concept, feed-forward control yields much faster correction than feedback control does, and in the ideal case, compensation is applied in such a manner that the effect of the disturbance is never seen in the controlled variable, the process output. Now look at the figure on the right. A skillful operator of a direct contact water heater could use a simple feed-forward strategy to compensate for changes in inlet water temperature by detecting a change in inlet water temperature, and in response to that, increasing or decreasing the steam rate to counteract the change. This same compensation could be made automatically with an inlet temperature detector designed to initiate the appropriate corrective adjustment in the steam valve opening. The concept of feed-forward control is very powerful, but unfortunately it is difficult to implement in most process control applications. In many cases, disturbances cannot be accurately measured, and therefore pure feed-forward cannot be used. The main limitation of feed-forward is due to our inability to prepare perfect process models or to make perfectly accurate measurements. Because of these limitations, pure feed-forward would accumulate the errors in its model and would eventually self-destruct. The main limitations of feedback control are that feedback cannot anticipate upsets but can only respond to them after the upsets have occurred, and that it makes its correction in an oscillating, cycling manner. It has been found that combining feedback and feed-forward is desirable in that the imperfect feed-forward model corrects for about 90% of the upset as it occurs, while feedback corrects for the remaining 10%. With this approach, the feed-forward component is not pushed beyond its abilities, while the load on the feedback loop is reduced by an order of magnitude, allowing for much tighter control.
Hi, I am going to take over this part onward. Next, we are going to demonstrate simple simulation to compare the response of feedback control and feedback plus feedforward control.
This simulation simulates the dynamic behavior of a liquid level in boiler drum. Feed water flow stream is manipulated via a control valve. Assume that the liquid's temperature inside the boiler drum is constant provided the liquid level achieved set point. Steam outstream is assumed to have certain operating flow rate, which is 100 cm² per second, based on demand from downstream processes. Therefore, any sudden change on demand on downstream processes introduce a disturbance for boiler system. The topmost plot shows changes in liquid level set point. Middle plot shows flow rate disturbance at time equals to 35 seconds. The bottommost plot shows the liquid level response inside boiler drum. Black curve is for feedback-only system. Red curve is for feedback plus feed-forward system. From the plot, it can be seen that feedback plus feed-forward can limit the effect of disturbance significantly.
As a concluding remarks, it has been found that combining feedback and feedforward is desirable in that the imperfect feedforward model corrects for about 90% of the upset as it occurs, while feedback corrects for the remaining 10%. With this approach, the feedforward component is not pushed beyond its abilities, while the load on the feedback loop is reduced by an order of magnitude, allowing for much tighter control. That's all. Thanks for watching.